Hello, and here we are again. This is the fifth video out of six, so 5/6 of the way through after this one, on the topic of forces and motion. So today it gets quite a bit more complicated. We're going to consider connected bodies and connected particles. So whereas before we've just been considering forces and motion acting on one particle in isolation, now we need to consider what happens where we have one or more particles combined, typically via a rope or a string, for example. And so we're going to apply here Newton's second and third laws, which I'll talk to you about later on. Before that, though, let's have a few warm-up questions to get us in the mood and to get our brain juices flowing. So here they are, questions 1 to 4, obviously. So try these on your own independently, and then when you're ready, press play so that you can see if your solutions match up to mine. And if not, make any corrections where necessary, or if so, give yourself a nice big tick. So let's have a look now at question number 1. So for number 1, what we have is a horizontal force of 60 newtons acting along a rough horizontal plane which is pulling an object A of mass 10 kilograms, which importantly is modelled as a particle. So given that object A is acted on by a constant frictional force of 20 newtons, draw a force diagram showing all forces acting on A. Well, it says here that it's a rough horizontal plane. So horizontal means we're just going to go left and right, like so. It's a particle, so there's going to be no air resistance. So what I'm going to do here is just add in the particle. Fancy colouring this in, actually. I think I'll colour it in a yellow colour. I'm going to put it on the surface like so. Now we can start about thinking the forces acting on this. So it's being pulled along by a horizontal force of 60 newtons. That's one thing we've been told. So just underline that so we can add it in. So because of that, I'm just going to draw an arrow. We can say that's 60 newtons in magnitude. Now it has a mass of 10 kilograms, so it'll have a weight associated with it. The weight of the object, it'll be 10g. So I'm going to do an arrow going downwards. I'll just call that 10g. As well as that, there will also be a reaction force, a normal reaction force, from the surface pushing back up, equal and opposite to the weight of the particle to balance out its weight so it doesn't fall through the ground or float up, which obviously would never happen. So going up, I'm just going to do a normal reaction force and call that 10g. Can't seem to get my arrowhead to be straight, this is quite annoying. There we go. That's going to be 10g in magnitude. But also as well, it says here that there's also a frictional force of 20 newtons acted on. So what I'll do here is just add this in as well. So the friction will always resist the motion. So I'm just going to do a line here. Not doing very well with these lines today. So I'm going to do a line here going backwards. I'm going to label that 20 newtons. So there's 4 main forces. For weight, the force dragging it along, the frictional force resisting the motion, and the reaction of the surface against the body. Part B, use Newton's second law to calculate the acceleration of A. And so, obviously there's going to be no net force going up or down. The 10g up cancels the 10g down. So we just need to apply F equals ma horizontally. So the overall force going to the right is 60 minus 20. So that's the resultant force. Obviously that's 40, but I'm including 60 and 20 so you can see where I'm arriving of a number 40. So that's going to be equal to the mass, which is 10 multiplied by the acceleration. And of course, what you should know is that we've been told the mass in the question, it's a mass of 10 kilograms. So 60 minus 20, like I say, is 40. So 40 equals 10a. Therefore, the acceleration will equal 4 meters per second squared on this particle. So that's question 1. Let's now see question 2. So question 2, we have a diagram showing an object of mass 10 kilograms connected to a light inextensible string. Given that the object is accelerating upwards at 0.2 meters per second squared, find the tension T in the string. So for this one, we just need to apply F equals ma going upwards. So let's just write that down so we can know what we're doing. So F equals ma applied vertically. So the overall force in the upwards direction will be T, which is going up, minus the W, which is resisting the motion. W is acting against the tension, which is driving this acceleration, so we do minus W. So T minus W equals the mass of the object, which is 10, multiplied by the acceleration of it, which is 0.2. So we just need to see where these have come from. So this is T, W is resisting the motion. So T minus W gives us the resultant force, so that is the resultant force. 10 is the mass of the object, and we've been told that the acceleration is 0.2. So we know where all these numbers have come from, should be no surprise, but I'm just labelling them on here. So we can actually go one step further with this. I've labelled it as W, but W equals mg, of course. So T minus W is the same as T minus 10g. So the weight, I'm just substituting in what the weight is in terms of the mass and the gravitational field strength of the Earth. 10 multiplied by 0.2, that's just going to be 2. So therefore T is just going to be 10g plus 2. Now we need to remember that g is 9.8 unless a question says otherwise. So 10 multiplied by 9.8 plus 2 gives us 100 newtons. So that's question 2. Let's now have a look at the third one. So here we have a mass, 5 kilograms. It's accelerating at 1 plus 2j meters per second squared. And to calculate the magnitude of resultant force acting on the particle. So here what I'm going to do is just draw in this particle. So there's a particle. It's accelerating at I plus 2j meters per second. So the acceleration, I means to the left, I means to the right, j means going up. So I plus 2j means 1 to the right, 2 to the left. So it's accelerating in this sort of direction. So I'll label in these components. So that's 1i, that's 2j, and the acceleration is in this direction. So the magnitude of acceleration is what we need to work out first. So we're just talking Pythagoras. So what's the size of this hypotenuse? Now we know that this is 1 and that's 2. Well, it's going to be 1 squared plus 2 squared, all square rooted. So 1 squared plus 2 squared, all square rooted, is simply going to give us root 5. And because that's not the final answer, we want to work out the magnitude of the resultant force, I'm going to leave it in exact third form for now. Now we can apply F equals ma. Okay, so the magnitude of a resultant force, okay, so we can now use this idea of magnitude to help us. So magnitude of resultant force is actually this. And we can adapt F equals ma on the right-hand side as well, so that the A is actually like that. So the magnitude of the force is the mass multiplied by the magnitude of the acceleration. So the mass, we're told, is 5 kilograms, so we can add this in. And the magnitude of the acceleration we worked out to be root 5. So it's just 5 multiplied by root 5. And now at this stage, we can actually give a numerical answer if we want. So 5 multiplied by root 5, that gives us, to 3 sig figs, 11.2. So we have 11.2 newtons as the magnitude. Now question 4. We have to solve the equation sine 2x equals 1/3 in the interval from -180 up to 180, giving answers to 1 decimal place. So what we need to do here is notice that sine of 2x isn't the most straightforward ones to solve. So what I'm going to say here, I'm going to make a substitution. I'm going to say let 2x equals big X. Okay, so I'm just going to be replacing the 2x with a big X. Then when we do that, because we want x to be in this range, from -180 to 180, then we want 2x, if we just double everything in the inequality, so double x to get 2x, double 180 to get 360, double -180 to get -360. But of course, 2x's is the same as just big X now. So the range we're wanting for our new variable, big X, is now between -360 and 360. So let's go on and try to solve this now. So we want sine big X to be 1/3. So we can get a principal value for this by using the calculator. So the principal value is going to be sine -1 of 1/3. Now, we need to give our answers ultimately to 1 decimal place. Here, I'm going to round off to a bit more, so we don't incur any rounding error. But if we do shift sine -1, then 1/3, press equals, I'm going to give this to 19.471. So that's our calculator value. Now, of course, there's going to be more values to find. We could have big X going from anywhere from -360 up to 360. So it's very likely that there'll be more solutions to find other than just 19.471. So at this stage, when we're solving these types of trig equations, we need to remember what diagram we can use. And that diagram is called a cast diagram. So here's one I made earlier. So what I'm going to do here is add into the cast diagram 19.471. So this is the way I tend to do it. I just do a big cross, going for the origin of the cast diagram. 19.471 is a positive angle made with the x-axis and this line, so 19.471 is this one here. So our principal value is in range, so this is a valid solution in itself. So I'm just going to colour this like a green colour, because we know that this is valid, and that's absolutely fine. However, sin x is 1/3. So sin x is positive. So we need to consider next which quadrants sin x is allowed to be in if our sin x is positive. Well, sin is positive in the A quadrant, because A stands for all positive between 0 and 90, and sin is also positive in the S quadrant. So we can begin to write down the solutions for x. So we've got here that x equals 19.471, and that's absolutely fine. But it's not the only one. So if we imagine looping round to this one here, and I'm going to add in as well, by the way, we know that all the acute angles between the x-axis and these lines will be 19.471. So I'm just going to add these in as well. So like I was saying, a valid one would also to be starting from here and loop around until we get to there. That would take us to this value here in the second quadrant where S is also positive. So this angle here is almost 180. It's 180 apart from this 19.471. So if I just did 180 minus 19.471, I see that it's 160.529. So that's a valid angle as well, so I can add this in. We could also, though, go the other way around. So one thing we've not considered yet is there's different ways of getting to S and A. So we could also go round in the negative direction clockwise. So another alternative we could do is to go here. That would be minus 90, minus 180, minus 180, minus another 19.471. So minus 80 minus another 19.471. That would take us to minus 199.471. That's another valid way we could get to this S quadrant where S is positive, which is what it actually is. There's also another way we could get to where sin is positive. We could get to the A quadrant as well, and we can get to the A quadrant by starting off here and going almost all the way around this circle. So minus 90, minus 180, minus 270, all the way around to here. And so that one is actually minus 360 plus 19.471. It's almost a full negative 360 apart from this 19.471. So what we do here, it's 19.471 minus 360. It's minus 340.529. And these are the only solutions we have. If we went round again and did like another loop of this diagram, we'd be going too far out of the range. We'd be going either lower than minus 360 or more than 360. So these are the only solutions we have. So what we do next, to go from big X to just 1x, big X is 2 x's. So to go from big X to an x, we just divide by 2. So what we need to do is we divide these solutions for big X by 2 to get the solutions we need for normal little x. So what I'm going to do here, I'm going to put these in order, just so it reads nicely. So what we're going to have now is our final answers. Is little x, our smallest one here is minus 340.5. So if we divide that by 2 and give it to 1 sig fig, that becomes minus 170.3. The next one, minus 199.471. If we take that and divide it by 2, that's going to give us minus 99.7 degrees. Then 19.471, take that and divide it by 2, that's going to give us 9.7 degrees. And finally this one in red, 160.529, take that and divide it by 2 to 3 sig figs, or 1 decimal place, we get 80.3 degrees. And that's it, quite a long warm-up really. Question 4, these cast diagrams can take a long time, but it's worth revising them, so that's why I threw it in. Let's now have a look at the next part of this mechanics course. So let's see what's in store. So I'm just going to jump straight in with an example on connected particles. So what we have here is a light inextensible string connects 2 particles P and Q, and these have masses of 3 kilograms and 7 kilograms respectively. So let's start to draw in this situation. We're already as well been told that it's a horizontal force of 60 newtons pulling them along a horizontal plane. So we know here actually that it's going to be a situation where it's moving horizontally. So we've got P and Q, so I'm going to just add in here P and Q. They're connected by an inextensible string. Inextensible just means it can't stretch, so it's the same length all the time. It's not like an elastic band. And as well, they've got masses of 3 kilograms and 7 kilograms, so that means they've got weights associated with them as well. So for weight of P, that's going to be 3g. For weight on Q is going to be 7g. It's been pulled 60 newtons, so 60 newtons is pulling particle Q. So I need to label in a force of 60 newtons on Q, which is pulling it over here. Okay, but we're also told that they're experiencing, these particles, constant frictional forces. So one frictional force is 8, so it goes P, Q, 8, 12. So P has a frictional force of 8, which will always act in direction of which the motion is trying to go in. And Q has a frictional force of 12, which again will work against the motion. So this 8 Newton force here will end up going against P. So 8 newtons is going that way. And the 12 newtons force will be acting against Q, going back this way. Now, just reading ahead in this question, it does mention a tension in the string. Now, tension is a strange force. Tension always acts away from the object the string or rope is attached to. So tension, even though the tension's acting in the same body in the string, relative to P, the tension will be going away from P, But relative to Q, the tension will be acting away from Q as well, so it's acting in different directions along the same body. So that is a bit of a strange one to get your head around, but there you go. I can label these both capital T because the tensions are one and the same, for the same magnitude at least, different directions. We've almost finished labeling this force diagram. One thing we've not labeled yet though is the fact that these objects P and Q will have a normal reaction force. And what I mean by that is that they will have a reaction from the ground, keeping them up, and it will be equal and opposite to their weights. So going upwards at P will be a reaction of 3G, going upwards at Q will be a reaction from the ground upon Q of size 7G. Now at this stage, what I want to do is just show you a way you can do it by considering P and Q separately. This is why the box for A looks a bit misshapen. I'm going to show you just another way of doing it here. So the point I'm trying to make in advance is, as long as you consider the system carefully, either just pick on individual objects one by one, or the whole system considered as one, the answer will still drop out as long as you're careful. So I'm just going to section this out here. Okay, so if I just consider first of all Q. In fact, no, I'll do P first. So considering P, which is this one here. By the way, hopefully you noticed already that this time round the vertical forces cancel. Okay, 3G cancels with 3G going up. There's no acceleration up or down. The acceleration we're going to be dealing with is just horizontally. Now, part A, it's asking us to find the acceleration of the particles. We've got forces labelled. We know the masses of the particles. Forces, mass, and acceleration. How does that relate? Should be thinking F equals ma. So, well, let's just do, considering horizontally, so just thinking of the horizontal direction, let's think about F equals ma for P. So P and Q are both accelerating in to the right hand side. Okay, so in fact what I'll do, I'll label this in as well. So the acceleration is that way, because it says they're being pulled along by the 60 Newton force. So the acceleration will be in this direction. So I'm going to label that A. So the forces pushing to the right on P, and in the direction of this acceleration is just T. So we've got T, then minus 8, so T minus 8 equals a mass of P multiplied by the acceleration of P. Well, the mass of P is 3. The acceleration of P, we don't know, I'm just going to leave that as A. So now we're going to do the same for Q. So F equals ma for Q. So for Q, we've got a force going to the right of 60 newtons. But we've got two forces holding it back. So we've got a T going the other way and 12. So 60 minus T minus 12. So that's going to be the overall resultant force going to the right. 60 take away these two holding it back. That'll be equal to the mass of Q, which is 7, multiplied by the acceleration of Q, which will be the same as the acceleration of P, because these bodies are connected by a string which isn't stretching. So that's going to be 7a. So now what we can do here, if we look carefully, is consider these as two simultaneous equations. So if we've got the top and the bottom and we add these, t on top minus t on the bottom, the t's will cancel. Now in terms of the numbers, minus 8 plus 60 minus 12. Well, let's just sort out this bottom here first. 60 take 12 is 48. So 48 plus minus 8, that's going to give us 40. So we have 40 equals 3a plus 7a, that's 10a. Now if we divide both sides by 10, therefore a must be 4. 40 divided by 10 is 4. So therefore a is 4. Now you might be still thinking, why did I do this dotted line here? What's the other way of thinking about it? Well, I'm going to explain now. What I've done here is I've considered initially P and Q to be separate objects, which is absolutely fine. This solution of A being 4 is correct, but it's not the only way it could have been done. What we could have done is considered the system of P, the string, and Q as one whole object considered as one. So sometimes we can consider different components of a system together as one, which is absolutely fine. So if we were to do that, for example, the mass of the system of P, the string, and the Q would be the mass of P plus the mass of Q, which should be 10. The forces going to the right in total for P and Q would be 60. You might be thinking, what about these tensional forces? Well, if we consider a system of objects grouped as one, the internal forces acting within the system cancel each other out. So these forces T, which are acting amongst P and Q themselves internally in the middle, would cancel out. They'd be equal and opposite all the way throughout the string, so they wouldn't matter when considering P and Q as one. So to the right, all we'd have would be 60 acting externally to PQ, and acting externally to PQ on going to the left, and be the 12 and the 8, which should be 20. So let's try and picture this now. So as I say, the alternative is considering it as one whole body. We'd have something like this. So we'd have 60 going to the right from here, and the combined frictional force of 20 going to the left. Yes, I could label in the total weight going down and the reaction going up, but like we said before, the motion is horizontally, so in terms of applying F equals ma, we just need to consider horizontal forces. So on that note, let's apply it. So let's apply F equals ma going to the right. So the overall force going to the right is 60 minus 20. I've called it PQ, the whole thing. So the mass of PQ is the mass of P, which is 3, plus the mass of Q, which is 7. So it's 3 plus 7 multiplied by whatever the acceleration is. So now we can neaten this up. 60 minus 20 is 40, and 3 plus 7 is 10, so 3 plus 7a becomes 10a. And as you can see now, we get exactly what we had from before, so therefore a must be 4 meters per second squared. So now you may have noticed that this t minus a equals 3a became highlighted. Now this is for part B. So part B, it asks us to find the tension in the string. So on part B, we can link back to part A. So from part A, we got here that t minus 8 equals 3a. So although doing it this way happened to be a bit longer and took quite a bit of work, it's actually useful now because we've got some forces involving the tension, which we can now use. We know A now, so if we sub in A, we can actually drop out what the tension must be. So T minus 8 equals 3 times 4, which is 12 obviously. So therefore the tension will simply be 12 plus this 8, which will be 20 newtons. Finally, for part C. Now these are common 1 or 2 mark questions in exams, but all the marks you get the better. Explain how the modelling assumptions that the string is light and inextensible have been used. So there's a couple of things we could say here, really, for these. So what I'm going to suggest is something like this. Because it's light, we can say that the string has a mass that is negligible. It's insignificant. So by considering the string as being light, we don't need to really consider it as an object in its own right. We don't need to apply F equals ma for the string. It makes it less complicated if we just think, well, it's light, so the mass doesn't really matter, it's so small. The fact it's inextensible is a bigger one. Because it's inextensible, what we can assume with the modelling is that the tension is constant throughout the string, and the acceleration, therefore, is the same. So, for example, if I had like a bungee cord attached to, imagine it attached between 2 people, one person could be running off in the other direction. It'd only be after a while that the bungee would get tight and drag the other person along, then we'd have some sort of amusing rebound effect. So if this was elastic, the tension wouldn't be the same all the way throughout. Okay, but because it is inextensible, it's not elastic, that allows us to model the tension as constant throughout. And because the tension is constant throughout, the acceleration between the connected bodies is also the same. So this wouldn't work if you had some sort of elastic band or bungee cord. The motion would be very complicated there indeed, and wouldn't be constant acceleration at all. So let's just move forward now. Newton's third law. So let's state it, then we can talk about it. So Newton's third law states that for every action there is an equal and opposite reaction. So this means when you've got 2 bodies A and B that are in contact, if body A exerts a force on body B, then body B exerts a force on body A that is equal in magnitude and acts in the opposite direction to the other body. So before we get off with a worked example, let's consider an example with just 2 objects A and B in equilibrium, where object A rests on top of B, which in turn is at rest on a flat horizontal surface. So that's what we've got. A stacked on top of B, which in itself is stacked on top of a floor. Now let's consider some forces. So, the force exerted on B from A. So at this point now, what we can do is begin to label on what we've got force-wise. So we've got forces acting on A, and of course we've got forces acting on B. So I'm just going to sketch these in now. So acting downwards at A will be the weight of A. I always get these arrows a bit wonky, sadly. It's a small thing, but very annoying. So that's going to be the weight of A going down. Likewise at B, going down at B, will be the weight of B. Between A and B, A will be having a reaction on B. So if any force going down, because it's in equilibrium, on A, is the weight of it. But A isn't accelerating vertically, and so it's got to have some reaction force balancing out its weight. And that's going to come from the upwards reaction. Now this can be a letter R, alternatively sometimes it's a letter N. So it's going to be a reaction there. So it's going to be a reaction force, which I'm just going to say reaction force of B on A. So let's consider the force exerted on B from A. Well, the force exerted on B from A is essentially the weight of A, which is pushing it down. So that's going to be equal to the weight of A. But the force exerted on A from B, so on A from B is the reaction force. So reaction force I've labelled reaction of B on A, but that must be equal and opposite to the weight to keep A in balance vertically. So that's the same as the weight of A. So as you can see here, the size of the force on B from A is the weight of A, and as well as that, the force the other way around, the force on A from B is again the same as the weight of A. So indeed, for every action, there's an equal and opposite reaction. So A is exerting a force on B equal to its weight. Likewise, A is having a force exerted on it from B, which is equal and opposite to the weight of A. So let's go forward now and think about this one. So what's the force exerted on the surface from B? Well, if we have a look at this here, and we can now consider it as like two rectangles, two squares, but considered as one. Obviously we need to know though that ultimately this force on the ground is acting through B, because B is in contact with the ground, isn't it? So if I just consider this as just one particle, just for a moment. Okay, so that's A, and then I'll do B sat on top. This isn't meant to be to scale. I suppose you could argue it looks nothing like in terms of size of these questions, but never mind. I'm going to consider this as like one whole object. So I'm going to call this here AB. So if you think about AB, what's going to happen with AB is it's going to have a force acting downwards, okay, and that's going to be the weight. That's going to be the weight of A plus B. In other words, it's going to be the weight of A plus the weight of B. But as well as that, there's going to be a reaction force, which will be equal and opposite going this way. And that reaction force, reaction of the ground on B, reaction of surface on B. So again, if you see here, I've considered it as one whole particle, A and B combined. Sometimes it's more useful to do that rather than considering it just as two separate things. So the force exerted on the surface from B, well, the surface is holding up B and A on top of it. It's supporting the weight of A and the weight of B. So for this one, it's supporting weight of A and the weight of B. The force exerted on B from the surface, though, for reaction, because this object B and A isn't flying up or falling through the ground, the reaction must be equal and opposite to the combined weight. So here, the force exerted on B from the surface is the reaction of the surface on B, which must be equal and opposite to the combined weight to keep it in equilibrium. So to conclude, the force on the surface from B is WA plus WB. The force on B from the surface is WA plus WB. So for this action here, there's an equal and opposite reaction here. So the forces are equal and opposite. So that's Newton's third law using a simple example. Let's now have a look at some harder examples using Newton's third law, which we can talk through together carefully. Here's a worked example which has been adapted. So we have a scale pan. You might be thinking, what on earth is a scale pan? Well, a scale pan, all it means is it's like a hollow device which is often hoisted up, for example, on a pulley or a lever, which carries things. So the scale pan is this triangular thing here, which is hollow, which is just a pan for carrying up objects, in this case, A and B. So the scale pan itself, this rectangle, has a mass of 0.5 kilograms, and it's attached to a vertical, light, inextensible string here. The scale pan carries two masses, A and B, of mass 2 and 3 kilograms respectively. So I'll just color code that. So A is 2 kilograms, and B is 3 kilograms. So A rests on top of B, like was shown. If the scale pan is raised vertically using the string, has acceleration 0.1 meters per second squared. So I'm just going to label on here the acceleration, just because we know it, so we may as well use it. So that acceleration here is 0.1 meters per second squared. The first question is to find the force exerted on mass A by mass B. And so what I'm going to do here, I'm just going to consider this separately. I'm just going to think about mass A on its own. So if I just get a rectangle, and I'm going to pretend it's mass A. Okay, so that's mass A. I'll colour it in yellow as well, like we've got there. So let's now consider all forces acting on mass A. So obviously going downwards, it's going to have the weight acting on it. So the weight is going to be its mass times g. So the weight going down is going to be 2g. I'll just move this up a bit actually, so I've got plenty of space. And going up, acting upwards from A, is going to be the reaction, which is going to be the force exerted on mass A by mass B. So I'm going to call this a normal reaction force. I'm going to call this N. And those are the only forces acting on A. Anything going down on A is its weight. Nothing else is actually physically pushing it down. And pushing it up in reaction to its weight is this force N. So what we can do here is apply F equals ma, going upwards. So the overall force going upwards is going to be N minus 2g. That's the overall force going upwards. So according to Newton's second law, that's going to equal the mass of A multiplied by the acceleration of A. Well, the whole system's accelerating at 0.1. So we may as well label in this acceleration and just make it really clear. So 0.1 going up, which comes from this information here. So the acceleration is going to be 0.1, and the mass of object A is 2. So n minus 2g is going to equal 2 multiplied by 0.1. So just rearranging this, so therefore we can see that n is going to equal 0.2 plus 2g. So if we get the calculator and try this, what we're going to get is 0.2 plus 2 times 9.8. And that's 19.8 newtons. So that's the reaction on mass A from mass B. Now part B I've split into two different boxes, so I'm going to show you how we could do part B in two separate ways. So here what we're wanting is to work out the force exerted on the scale pan by mass B. So what we've got here, I'll just label in mass B again, and I'll do this in a green colour. So what will happen is B will exert a force on the scale pan, and equal and opposite to that, at the point of contact, the scale pan will exert a force back onto B from Newton's third law. There'll be an equal and opposite force acting from one to the other. So I'm just going to sketch in B and B alone. So I'm just going to consider B on its own. So I'm just going to nick over here what we had for mass A and transfer it in a different colour over here, which we're going to call mass B. So what's happening on mass B? Well, like I mentioned just now, according to Newton's third law, every action has an equal and opposite reaction. So what happened on part A, what we've realised, is that mass B exerts a force of N on mass A. So therefore mass A will exert this same force of 19.8 newtons onto mass B. And so actually what we're going to have here on mass B is two forces acting down. Okay, so acting down on mass B is obviously its weight. Its weight is 3g. But again, we have the equal and opposite force that mass B was exerting on A. Now mass A is exerting the same equal and opposite force on mass B. So whereas on A, N was going up, because it's going to be equal and opposite, on B, the force A is exerting on B will be N going down. Of course, now luckily, we know what N is. So N is 19.8 newtons. So obviously, on B, there'll be a reaction from the scale pan on B, pushing B back up. So I'm going to label this R, and I'm labeling it R so it doesn't get confused with this N. So one way we can do it is to consider F equals ma vertically. So F equals ma going upwards. So the overall force going upwards is R minus N minus 3g, and that's going to equal the mass of B. The mass of B is 3 multiplied by the acceleration, which again we know is 0.1. So this can be neatened up quite a lot now. Okay, we essentially know what N is. N is 19.8. So we can just say now what R is. Therefore R is going to be this 3 times 0.1, which is 0.3, plus 3g, plus N, which is 19.8, so if we just do this now, we get 0.3 plus 3 times 9.8 plus 19.8. And that gives us 49.5 newtons. So that's one way we could do it, and I think that's probably the most obvious and straightforward way, but it's not the only way. It's now worth considering that this 49.5 Newton force, this is the force exerted on mass B by the scale pan. It's not, it would seem, the force exerted on the scale pan by B. However, it actually is via Newton's third law. So what we're saying here, because the scale pan is pushing up on B with 49.5 newtons, then mass B will push equally hard in the opposite direction back on the scale pan. Every action has an equal and opposite reaction. So because we know Newton's third law, we can say actually this reaction on B from the scale pan will be the same as the reaction on the scale pan from B. So that still is 49.5 newtons. And I did mention, of course, once again, that there's another way of doing this. What we could do as an alternative is consider forces on A and B combined. So we could consider A and B combined. So if we did that, I'm just going to call this big blob here AB. So obviously on AB, there's going to be a weight, which makes it go downwards. And there's going to be, if anything on AB here, pushing it up, if anything in contact to push it up, is the scale pan itself. So what I'm going to do here, if I can get this arrow straight, I'm just going to call this here the reaction, and here's the weight. So F equals ma going up, we'd have that R minus W equals the total mass, so the mass of A plus the mass of B, multiplied by the acceleration. So that's going to be 2 plus 3 multiplied by the acceleration. So of course, the mass of A is 2, the mass of B is 3, and the acceleration is 0.1. So therefore, the reaction, 2 plus 3 is 5, times 0.1 is 0.5. Then plus the weight, well, the weight will be the total mass of A and B multiplied by G. Total mass of A and B is 5, so we're going to add on 5G. So 0.5 plus 5G, where G is 9.8. That gives us 49.5 newtons again. Same result, just different approach. Now C, I'm going to show you the same thing again, the fact that there's also two approaches for part C. So for part C, what we need to do is to find the tension in the string. So what we can do is consider the whole thing as one. So we can consider the whole system as one. As one mass. And if we did that, what we'd have is the scale pan, which would be obviously triangular in shape. So I'll get this filled in. I'll just call this, won't call it anything actually, just have that as a black colour. So obviously going down on the scale pan, anything going down on it is the weight, and going up, acting upwards on the scale pan, is obviously this tension in this string. So again, we can consider F equals ma going in the vertical direction. So F equals ma vertically. So the overall force is going to be T minus W. That's the overall force going upwards. Now W is going to be the weight of the whole thing. Okay, so T minus W is going to be the mass of this all plus the, multiplied by the acceleration. So I've just highlighted here, the mass of the scale pan is 0.5. So the total mass of everything is going to be 2 for A, 3 for B, 0.5 for the scale pan, multiplied by the acceleration, which is 0.1. So just labelling this in here. So 2, that's A. 3, that's B. 0.5, that's the weight of the scale pan itself. The mass, sorry, of the scale pan itself. And the acceleration is 0.1. So if we rearrange this now, so therefore T, all this added together is 5.5, okay? 5.5 multiplied by 0.1, that's 0.55. And then the weight of everything is going to be the combined mass, which is 5.5, multiplied by G. So if we work this out now, we're going to get 0.55 plus 5.5 multiplied by G, which is 9.8, and that gives us this figure of 54.45. So that final answer we get is 54.45. That, however, like I've said, isn't the only way it could be considered. We could also consider, alternatively, the forces acting on the scale pan. Okay, so if we do that, forces acting on the scale pan. So I'll just call this an alternative. I'm going to call this forces acting on the scale pan. So again, just considering this scale pan like so, it's got a tension on it going upwards. As well on this scale pan though, it's got its own weight, so going down on the scale pan is its weight, which is 0.5 G. As well as that, also, from one of the earlier parts of these questions, we also saw this one here, that there is going to be a reaction acting on the scale pan from mass B. There's a force exerted on the scale pan by mass B, and the force from B was 49.5 newtons, which goes down relative to the scale pan. So actually, on the scale pan as well, there's another force going down, which is 49.5. So now, if we just consider the scale pan, which remember is hollow, the scale pan on its own is just 0.5 in terms of mass, we can now apply again F equals ma in the vertical direction. So the overall force going up is this tension, T, subtract the forces working against it. So its weight, the weight of the scale pan is 0.5 G. The reaction from B is 49.5, so minus 49.5. That's going to equal the mass of the scale pan, which is 0.5, multiplied by the acceleration of the scale pan. And the acceleration of the scale pan is the same as acceleration as everything in this system, 0.1. So again, just to colour code where everything's come from. So that's 0.5 for the scale pan, and 0.1 is the acceleration. So if we rearrange this, again, we'll see that T is going to equal, well, 0.5 times 0.1, that's going to be 0.05. Then plus 49.5 plus 0.5 G. They'll come out the same, but just to prove it to you, so 0.05 plus 49.5 plus 0.5 G. And again, you can see we get 54.45 newtons. And so obviously I've shown you alternatives. We only need one way of doing it, but that's worked example 1 done. I'm now going to show you 3 different examples taken from real exam papers. So let's have a look at those now. So, worked example 2. So this is a real past paper example from many years ago, in fact. So it's just a load of information to begin with, so let's just read it first. So a car which has run out of fuel is being towed by a breakdown truck along a straight, horizontal road. The truck has a mass of 1,200 kilograms and the car has a mass of 800 kilograms. So it's just a bit too much to digest even already. So what I'm going to suggest we do is just draw a diagram out. So we've got a straight horizontal road, so we can just draw in a sketch of a road like so. And we've got a car, so I'm just going to do this as a rectangle, then a truck, like so. So we're told that the car has a mass of 800 kilograms, so its weight would be 800 g. So let's label in as we go. So that's where the 800 comes from. And the truck has a mass of 1,200 kilograms. So on the truck, that'll have a weight of 1,200 g. So what's happened here as well, they're connected together by a horizontal rope which is modelled as light and inextensible. So between them there's going to be a rope, and on that rope there's going to be a tension force acting away from each object. So this is the car, this is the truck. In fact, no, I won't do that because T I'm going to use for tension, so forgive me, that was maybe not the best thing to have labelled actually. We can tell these are the car and the truck by the weights, okay, so maybe a bad idea. So I'm going to label that the tension going one way, and relative to the truck it'll be pulling back. So that's the tension on the truck. So what else can we label in now? So we're told here the truck's engine provides a constant driving force of 2,400 newtons. So the truck is being thrusted forward by the force of the engine, which is 2,400. And that force is constant. As well though, we're told that there's resistances to the motion, and so the resistance to the motion of a truck and car are modelled as constant and of magnitude 600 newtons and 400 newtons respectively. So truck, car, 600, 400. So truck is 600. So there's a resistance on the truck of 600 newtons. So I'm going to label this on here. So I'm just going to do it from the road so it doesn't get in the way of this tension force. So that's 600 on the truck. And of course, also it says there's a force of 400 on the car, a resistive force acting against the motion. So, finally, we might be in a position to answer this question. What we could do, what we probably should do as well, is complete the diagram. Even though there's going to be no acceleration vertically, it's a horizontal road, any acceleration will be going left or right. We could label on here the reaction forces, which will be equal and opposite to the weights of the car and the truck. So the reaction force on the car from the road will be 800 G, and similar for the truck, the reaction force will be equal to the weight and opposite. So anyway, you want to find the acceleration of the truck and the car. So for part A, we can consider this as one body. So considering the whole system, what we're going to have is obviously the road. I'm going to draw on the object. So the total force going to the right is just with 2,400. Whoops, that isn't what I wanted to do. So I'll have to get rid of that, I think. This is what I wanted to do, 2,400. Now, the forces going to the left, remember, considering the entire system, we can ignore any internal forces. So we can ignore the tension force, that's internal, that's between the car and the truck. So the external forces are these resistive forces of 600 and 400. So 600 plus 400 gives a total resistive force going against the motion of 1,000. So we can now apply F equals ma going to the right. So the overall force going to the right is 2,400 minus 1,000. So that's going to equal the mass of the system multiplied by the acceleration. Well, the mass of a system is 1,200 plus 800. Multiplied by the acceleration. So that 1,200 has come from the mass of a truck, and the 800 is because that's the mass of a car. So if we just neaten this up a bit, 2,400 minus 1,000, that's 1,400. So 1,400 equals, well, 1,200 plus 800 is 2,000. So 1,400 equals 2,000A. Therefore, we can rearrange this by dividing both sides by 2,000. The acceleration will be 1,400 divided by 2,000. Which gives us 0.7 meters per second. Part B. Need to think about the tension in this rope. So we could do this either by considering the truck or the car. It doesn't matter which one you pick. Again, like I've shown you in the previous examples, there's more than one way of tackling any given problem. What I'm going to suggest is we just pick on going for the car. So if we consider the car, and again, it's on a horizontal road. So as you can see here, it's got a tension force going that way, which I'll call T. Its resistive force is still this 400, so I'll label this on again. And that's the only horizontal forces acting on this car. Yes, there's vertical forces, but the acceleration is just happening horizontally. So to be honest, we don't need to worry about those in this particular context. So again, applying F equals ma, going to the right-hand side. The overall force going to the right is T minus that 400. And that'll equal the mass of the car, which is 800 multiplied by the acceleration of the system, which we now know is 0.7. Give myself a bit more space. So that times 0.7. So rearrange this. So therefore T for tension is going to be 800 multiplied by 0.7 plus the 400. So if we work this out on, again, the calculator, surprise, surprise, 800 multiplied by 0.7 and then plus 400, that gives us 960 newtons. So that tension force will be the same on the truck and the car. Now part C. Part C is a bit trickier, so let's read this carefully. So it says, when the truck and car are moving at 20 meters per second, the rope breaks. Shock horror. The engine of the truck provides the same driving force, though, as before. The magnitude of the resistance to the motion of the truck remains a constant 600 newtons. What we have to do here is we have to show that the truck reaches a speed of 28 meters per second about 6 seconds earlier than it would have done if the rope hadn't have broken. Now that sort of makes sense in a way. If there's nothing holding the truck back, if it's not having to drag a car, it'll speed up quicker than what it would have done if it were having to carry the load of a car as well. So what we need to do is consider two different cases. So the first case would be that the rope didn't break. Okay, so let's imagine the rope didn't break, and in fact, I'm just going to move this dotted line and make it a slightly different dotted line. So let's just think about the first scenario. Just imagine everything was normal, the rope didn't break. Okay, so case 1. If rope didn't break. So if rope didn't break, we're told all forces remain constant, the acceleration would have been the same. If rope didn't break, then the acceleration would have been 0.7. So what we can do here is use that. So acceleration would have remained at 0.7. Nothing would have changed. S we're not interested in. What we are interested in is the car and truck were going at 20. So the initial speed is 20. The final speed is 28. So how long would that have taken to achieve? What would the time have been if the rope didn't break? We're not interested in the displacement. We're just interested in U, V, A and T. So what we can use here is V equals U plus AT. So what that gives us is V, which is 28, equals U, which is 20. Give myself a bit more space, never seem to give myself quite enough. 28 equals 20 plus A, which is 0.7 times T, which we're trying to work out. So therefore, T would equal 28 minus 20 divided by 0.7. So what does that give us? So 28 minus 20 all over 0.7. That gives us about 11.43 seconds. So if the rope hadn't have broke, it would have taken 11.43 seconds to have reached that speed. Obviously that case didn't happen. The actual thing that happened is the rope did break. So case 2, let's now consider the fact the rope did break. Now because a rope breaks, this alters the situation with the truck. So if the rope broke, which of course it did, we're going to have the truck here so it says here that the driving force remains constant, so its driving force would still be 2,400, pushing it forwards. However, the forces acting against the motion would be lessened. So whereas before there was this tension force When when the rope breaks, that tension force will have disappeared, and the only thing resisting the motion on the truck will be this 600 newtons force. So now we can apply F equals ma to this new system without the rope. So the overall force going forward would be 2,400 minus 600. So 2,400 minus 600 equals the mass of the truck, well, the mass of the truck is still 1,200, multiplied by the acceleration, which now will be changed. So therefore now, the acceleration, the new acceleration, 2,400 minus 600, that's 1,800. Divide everything by 1,200. We get now that the acceleration is 1.5. So now we can use suvat with this new increased acceleration. The acceleration is now greater because there's less holding the truck back. Okay, so now using suvat, now the acceleration is 1.5. We still need to find the time, t. The final velocity it reaches, we're still interested in how long it takes to get to 28. This rope breaks when we're moving at 20 meters per second. And yet again, we don't care at all about the displacement or the distance. So again, what we can use here is v equals u plus at. So therefore, the time taken is v minus u over a. V is 28, u is 20, so 28 minus 20 over our new a of 1.5. Let's see what this gives us. So same sort of calculation, but instead of a being 0.7, a is now 1.5. So divide all by 1.5, and we get roughly 5.33 seconds. So now, what I've highlighted in purple are these different times according to if a rope broke or if it hadn't have broke. So we need to show that it gets to that speed approximately 6 seconds earlier. So what we're trying to show here is how much shorter time is 5.33 as compared to 11.43. So we need to just conclude by saying, therefore it reaches 28 meters per second, 11.43 minus 5.53. So let's do that calculation now. So 11.43 minus 5.33, that's going to give us 6.1 seconds. So it reaches 28 meters per second, 6.1 seconds, which is about 6 seconds sooner than what it would have done had the rope not have broken. So that just proves it for us, and that's the question done. So quite an advanced worked example. Let's have a look at another couple which, don't worry, aren't quite as hard as that one. Worked example 3, we have a crate in a lift. So we're told here that the lift has a mass of 200 kilograms. It's been lowered into a mineshaft by a vertical cable attached to the top of the lift. Now, no matter what, this cable will have a tension which will be working away from the lift. So there'll be a tension force here going upwards. It also says there's a constant upwards resistance of magnitude 150 newtons on the lift. So as well as this tension force in the cable, there's also a constant force of 150 going up as well. The crate experiences a constant normal reaction of magnitude 473 newtons from the floor of the lift. Part A, find the acceleration of the lift. Well, we're told here what force the crate is experiencing from the lift. We also know the mass of the crate as well, so it might be a good idea to just start with the crate. So if I just sketch on this crate and then consider the forces acting on the crate. Obviously going down from the crate is going to be its weight, which is 55g. And will also be acting on the crate this normal reaction of magnitude 473. So it'll be acting in the opposite direction, pushing up from the bottom of the lift onto the crate from below. So again, that arrow isn't straight, which bugs me. That's going to be 473 newtons. So what we can do here is apply F equals ma going downwards. So F equals ma in the down direction. So the overall force going down is the weight of the crate minus this normal reaction on the crate. So it's going to be 55g minus 473. That's going to equal the mass of the crate, which is 55, multiplied by the acceleration. So again, we're told the mass of the crate is 55, so that's where 55 comes from here, and 473 is this normal reaction as well. So therefore, A is just going to be 55g minus 473 divided by 55. And if we work this one out, $55g means 55 multiplied by 9.8 minus 473, all of that over 55. That equals 6/5, which is 1.2 meters per second squared. It now says find the magnitude of a force exerted on the lift by the cable. Now there's two ways you could proceed here. One way will be to consider this whole system as one, or you can consider just the lift. So what I'm going to do, you could do it another way if you wanted. You could consider this as one whole body. So we're just going to consider now forces on the lift itself. Forces on the lift only. So the lift seems to be roughly square-shaped, probably a rectangle, but I'm just going to be rough and ready here. I'll call it a square. I know it's not, but never mind. So forces on the lift. So there's going to be forces acting down on the lift. So one of these forces is going to be the lift's weight. So the lift has mass of 200 grams. So its weight will be 200g. As well, what we've learnt today is Newton's third law. For every action, there's an equal and opposite reaction. So because this lift was pushing up on the crate with a magnitude of 473, the crate will also be pushing down upon the lift with magnitude 473 acting downwards. So this 473 will also come back to the lift from the crate from above. So we'll get a force going down of 473, equal and opposite to the force the lift exerts on the crate. There are also two forces going up. So one of these forces here, as you can see, is a tension. So T going upwards, and as well as that, there's this constant resistive force of 150 newtons going up as well. So I'll label this just 150. So now we can apply F equals ma on the lift going downwards. So F equals ma in the down direction. So the overall force going down is the sum of the downwards forces. So we've got 200g plus 473. Acting opposite the motion, going up, we subtract these forces. So subtract 150, and we subtract t. And that'll equal the mass of the lift multiplied by the acceleration of the lift. Well, the mass of the lift is 200, and we worked out the acceleration earlier. The acceleration of the crate will be the same as the acceleration of the lift because they're the same system. So the acceleration of the lift will also be 1.2. $200, got 473. We're subtracting that 150, and the mass of the lift is 200, which is where that 200 comes from. That 1.2 is from before. So we could neaten this up quite a bit. So 200g plus 473 minus 150. Let's just work that one out. So 200g, 200 multiplied by 9.8, plus 473 minus 150. So we've got 2283. So 2283 minus t equals 200 multiplied by 1.2. So 200 multiplied by 1.2, that's going to be 240. So therefore t will be 2283 minus 240. So if we just do this on the calculator, so minus 240, 2043, I'm going to round it to the magical three significant figures, so 2040 newtons. And that's correct to three significant figures. So let's now have a look at a fourth and final worked example. So finally, worked example 4. So we've got a car, mass 1,000 kilograms, so it's a ton, towing a caravan of mass 750 along a straight horizontal road. So already been given a clue here, it's going to be a case of acceleration going horizontally only. So I'm going to sketch in now some of the information. So it's going to do two rectangles, one for the car, one for the caravan. The caravan, get that one for the car here. So we've got the car, which has got a mass of 1,000 kilograms. So what I'm going to do, I'm going to put the car at the front. And then the caravan, I'll pop at the back. So it's on a straight horizontal road like this. And so the caravan's connected to the car by a tow bar. So again, tow bar is just the device used to actually hold it in place. So it's parallel to the direction of motion of the car and caravan. The tow bar is modelled as a light rod. So again, because it's modelled as a light rod, we don't need to consider the mass of this. That doesn't need to complicate anything else. The engine of the car provides a constant driving force of 3,200 newtons. So do an arrow going forward, 3,200 newtons. What else do we know? Oh, we're told resistances to the motion of the car and the caravan are modelled as 800 and R newtons respectively. So car, caravan, 800 R. So car must be 800 newtons. Just going to draw this on first of all. So we've got 800 newtons acting against the car. So I'm just going to draw a line there, call that 800 newtons. And again, For the caravan, there's a resistive force of R newtons, which needs to be calculated in a moment. And again, with this system, there's going to be a force, a tension in this tow bar. Tension acts away always from the object, so T there relative to the car, T here relative, so that's the caravan, and this is the car. So I'm just going to label this here at the top, car, this here, caravan. And again, for completeness, we could label in the weights. So the weight of the caravan is 750, the weight of the car is 1000 G. So 750 G for the caravan, 1000 G for the car. And of course the road will provide a normal reaction force of both of these, equal and opposite to the weights of both. So pushing up from the road will be 750 G for the caravan. Get that line straight if I can. There we go. And same for the car, only for the car it's going to be 1000 G. The same idea is what I mean to say, not the same value. So like I've mentioned before, the tension is an internal force relative to the system we're talking about. For part A, we need to work out R. Okay, so R is attached force-wise to the caravan. But looking at this caravan, we've got R, which we don't know, and T as well, which we don't know. So what we could do is just consider the whole system combined. So considering the whole system for part A. If we do that, the tensions won't matter, because the tension's an internal force relative to the entire system. So what we've got here, for the entire thing, we can just consider forces horizontally. Vertical forces cancel, they're equal and opposite. So the acceleration is going to be happening only horizontally. And in fact, we are told what the acceleration is. The acceleration of the car and the caravan is 0.88 meters per second squared. So we can label this on here. The acceleration is 0.88. Anyhow, so total forces for this entire system going forward. Well, the only force going forwards, which isn't one of these forces here which cancels, is just the force of the engine driving the car and the system forward. So that's 3,200 newtons pushing forwards. Now, pushing back, resistive forces, we've got two main ones. We've got R and we've got the 800. So we can label both on. So that's going to be R and, of course, the 800. Now, the mass of the whole system, the caravan and the car combined, is 1,000 kilograms plus 750 kilograms, so the total mass is 1,750 kilograms. So now we can apply F equals ma horizontally. So the net force going forward is going to be 3,200, subtract these two. So 3,200 minus R and minus the 800 as well. That's going to equal the total mass of the system, which is 1,750, multiplied by the acceleration, which we've been told is 0.88. So now it's just a case of simplifying this and working out what we can. So 3,200 minus 800, that's 2,400. So 2,400 minus r. And this number here, this 1,750 times 0.88, that's 1,540. So with a simple rearrangement, we can see what r is. R is going to be 2,400 minus 1,540. And that's 860 newtons. Now for part B, I need to find the tension in the tow bar. Now for this one we've got choices. We could either consider the caravan or the car. What I'm going to go for is just considering the caravan. So considering just the caravan. Okay, so if I just steal the caravan, which we've got here, yoink, pop it there. So again, the force pushing the caravan forward is just for tension. So that's T, which is what we're trying to find out, obviously. And resisting the motion is R, which is worked out to be 860 newtons. So we can label in R as being 860. And of course the mass of this caravan is 750 kilograms. We don't need to consider vertical forces because there's going to be no acceleration or motion vertically. So let's just work out F equals ma going to the right. So to the right we've just got T less the 860. That's going to be equal to the mass of the caravan, which is 750, multiplied by the acceleration of the system, which we were told earlier is 0.88. So a simple rearrangement, we'll get what the tension is. So therefore the tension is just 860 plus whatever 750 multiplied by 0.88 is. So again, get the calculator. So we've got 860 there already. So I'm just going to add on to that 750 multiplied by 0.88. And that gives us 1,520 newtons. And then we're done. So now it's over to you lot. So I know that was a slog, but you do need to practice some of these on your own as well. Hopefully that's given you a really thorough grounding in how to tackle these questions. So turn to page 171, exercise 10E. I want you to try question 1 first, then questions 4 through to 9. You know the drill in terms of finding help and asking for help. Good luck with them, let me know if you're stuck please, and I'll look forward to seeing you all soon. So for now, goodbye.